Recording is rolling. Welcome to Wednesday, October 20th. So, I need to do top scientist with you guys. This is top scientist for the quiz you guys just turned in a couple days back. So, look at all those top scientists in this class. Man, you guys rocked that quiz. You guys know I asked you. Yeah. Yeah, you guys know I asked you guys tough questions too. So, good job. Way to go. Way to go.
What?
Yeah. Thanks. Yeah, still got the quiz, then need that from you before I can give this back to everybody and post the solutions. Okay. All right, so you guys remember this table yesterday we started? We did the first two rows. Okay. We're going to do most of the rest of the table today. And then last few minutes of class, I'll tell you guys about hydraulic jump, switch over, look at a video demo, some stuff. Okay. But most of class today, we're going to be thinking about conservation of energy setups for all these different scenarios. Right? Now, you guys remember, energy can take different forms, and these are the forms that we care about, mechanical energy. Well, there's an energy transfer force in resistance, potential energy, MGH, energy stored in a spring, 1/2k squared, energy motion, 1/2 mv squared, and, well, we aren't going to deal with the last one yet, so I'm kind of that. All right, so we did these first two rows yesterday, so let's go on to the next one. All right, when there's a kid sliding down a hill and there is friction. So what is in what's considered part of the system? Now, I know this column says closed system, but I'm going to amend that for this one and also the next one. So do this, make a little note at the bottom, say this is actually an open system. And I'll tell you guys why in a minute. Same thing with the next one. Open system, when we eventually get to it. Okay. Those will be the only two that are like this on this whole packet. Okay. What a closed system is means that there's no external force and there's no work being done on or by the system. Right? So everything's self-contained. And if everything's self-contained, then energy is conserved. Right? If the system is open, though, what that means is that there can be an external force maybe doing work on the system, which means that there might be an energy transfer into or out of that system. Now, you can still do energy accounting, but say if there's work done by friction, some of the energy would go that direction, something like that. So kid sliding down the hill, the kid and sled as a combination, kid sled combo, it's like one giant object with some collective mass. Right? It's the fact that there's a gravity pulling down, right? So there's weight pulling down, right? Gravitational force. And as a result, there's a height change. That's all indication that what other object has to be in the system? The Earth. Yeah. Right. Which is also true for the examples we did yesterday. Right? The Earth is providing gravity pull, right? You might argue for the surface itself because it has friction, but there's a certain way I'm going to treat that. I'll treat that as outside the system. Okay? So the energy at point A is, well, if he's sitting on top of the hill at rest, what kind of energy is that? Potential energy. Yeah, you guys got that. MGH. Okay? And then by the time he slides down to the bottom, well, he would be on the move, so he's probably got some motion at point B, okay? But no more height. Right? So it's that dashed line, height 0. So there's no height at point B, no potential energy, but he is in motion, so that's what kind of energy? Kinetic, which is 1/2 mv squared. That building block at point B, right? Now there's a little bit more to this, but pause here for a moment, right? If there was no friction, then wouldn't that be the entire story? This energy at the top turns to this energy at the bottom, if there's no friction, right? And we've already solved that. Just look back 2 examples to the Galileo problem. Doesn't this look identical so far? Right? And the solution was square root 2gh. Right? And what I want you guys to get out of that is that if you have a frictionless surface, suppose you have an air hockey table. You guys have played air hockey, right? Let's say you lose a game, you're like, you tip up the table, so it starts to look like this. Right? And the air hockey puck is like sliding down with no friction. Right? How fast is it going to be going at the bottom? It would be going the same speed as it would had you just dropped it and it went straight vertical, just like the Galileo problem. So that's something you get out of a class like this, like physics. It's like, how do you navigate those formulas? Okay, so what I'm missing here is that between these 2 points, there's going to be work done by friction. So say minus work done by friction. Okay? And then let's set up an energy conservation equation and solve it from there. Okay. So the sum of energy at point A, I would normally say this. I would normally say equals the sum of energy at point B. But because it's an open system, instead I'm going to say the sum of energy at point A minus the work done by friction leaves you with whatever's left over is the energy at point B. Okay? Okay. This will be true for this one and also the next example, but then after that we'll just go back to closed systems. Okay, so the energy at point A, well, that's just your mgh. The work done by friction, wouldn't that be something like, sorry, I just gotta, don't run out of ink. Be something like the friction force times the distance moved, and the distance moved is L, isn't it? Right? And that leaves you with whatever is left over goes into kinetic energy, 1/2 mv squared at point B. That's okay, right? That's good? Now, here's where, well, you could go deeper on this problem. See that friction force? That friction force, remember how that's coefficient of friction times the normal force? And the normal force is the cosine component of the weight, right, which is related to mass. So there are 3 terms here. 2 obviously have mass in them because there's an m there and an m there. Right? That friction force, if you dig deep enough, is also related to the mass. So the masses could cancel out. We could go that way, but the purpose of this table is I want to keep it on like pretty general big picture. So let's just go ahead and solve for VB. We'll just do all the algebra at this point. Okay? Just treat friction forces, whatever force that is. So to isolate this VB, looks like a few algebra steps. I have to multiply it by 2. So mvv squared is equal to 2 mgh minus 2 friction force times length. Okay. And then divide by m. So vb squared is, oh, if I divide by m goes away, so it's just 2gh. And then minus 2 friction force length divided by m. Okay. Again, friction force is a function of them, so you could cancel that out if you dig deep enough, but don't worry about that so much. Okay. Then last step is take the square root. Square root 2gh minus 2 friction force times L, all divided by m. Okay. And that's true. That's a true statement. So I'll go ahead and treat that as the answer. So VB equals big ol' square root 2gh minus 2 friction force length over mass. Okay. Oh, so what have we done so far with this? Oh, we've identified the scenario. We've identified what kinds of energy. We set up the conservation equation. We took through a few algebra steps to isolate a variable to figure out the speed at the bottom. The last thing I want to do is see, can you guys read the music of this equation? Can you guys see what this equation is communicating to you? Maybe play around with variables. This is one of those tools in your mental toolkit that you should be able to get out of a physics class. Like, why are you taking physics, right? Like, where's this going to be useful? Well, it would be useful in like building a mental model of like, if I change this variable, how does that just change something like this? Like, for example, what if you got rid of the friction? If you got rid of the friction, what does this turn into? Wouldn't the friction force just go to 0? So this whole term would go to 0. And oh, look what that would be. Square root 2gh. Hey, it turns back into the Galileo problem, right? Like an air pocket table. Or what if you increase the length of the incline, so made it really, really long? Now that friction force would be acting over a longer distance, that would zap more energy out of it. Right? Something like that. All right. Next one, car brakes to a stop. Oh, this is one of these problems that you guys have seen before too. You guys know the story. So let's figure out what's wrong here. What is one object you think is important? How about the car, right? The car? Okay. You know what? I'm going to stop the list right there. You could argue the Earth because there's a force from the Earth, but that's being balanced out by the normal force, so I'm just going to ignore that. There's no height change, right? The car's not rolling up or down any hills. Okay. I'm just going to focus on the car. And the reason this is being an open system is because if I'm only focused on the car, well, the car is interacting with the road. There's a friction force from the road, so the road is acting, that friction is external to the car itself. Okay. So at point A, if the car's in motion, what kind of energy? Kinetic. That's 1/2 mv squared. Okay. Hey, you guys are answering these questions right, so you guys able to stay like a step ahead of me? Okay. If you can stay a step ahead of me, then it's a good sign that you know what you're doing. Okay. By the time the car gets to point B, well, it's stopped, right? So it has no kinetic energy. It hasn't rolled up any hills to get there, so it's not like it's converted to potential. There's no potential. I don't see any springs. what kind of energy, what kind of mechanical energy does the car have at point B? None. Zero. Hold on a minute. I thought energy was conserved. If you start with this much energy and we end up with nothing, wait a minute. It's an open system. So minus the work done by friction. So this minus this brings you to zero. Okay. By the way, what's the final speed of the car? Zero. That's the answer to the last talk. Boom. Okay. So in terms of this table, we're done with the table bits. But there's really another perspective I want to look at with this car. I want to ask a different question. I don't want to ask what's the final speed. That's too obvious. I want to ask what is the braking distance, because there's a couple of reasons I want to look at that. So let's do that. Sum of energy at point A. In this case, minus the work done by friction. This work energy theorem leaves you with whatever you're left over with, the sum of energy at point B, okay, which happens to be zero for a stopped car. Okay? So got your 1/2 mv at point A squared minus work by friction. Isn't that friction force times stopping distance? Isn't that just a version of this right here? Work is force times distance. Okay. That'll leave you with, 0 joules of energy because the car came to a complete stop. So, 0 joules of mechanical energy. What if the question was solved for stopping distance? Right. Now, here's where I will dig a little deeper because there's a specific thing I want you guys to see. Remember how friction force is equal to coefficient of friction times normal force? Okay. Here, like if I do a free body diagram. This car has a weight. This car has a normal force. And this car, if it's moving to the right with some initial speed, has a friction force acting opposite of that. Okay. And that friction force is coefficient of friction times the normal force. You guys remember that? Okay. So let me sub that in right here. So 1/2 mv squared minus coefficient of friction times normal force times the stopping distance. That has to go 0. Okay. But then one more thing. What is the friction force also equivalent to? Oh, it's just balancing the weight, isn't it? So I can sub that in right there. 1/2 mva squared minus mu mgx goes to 0. Okay. Okay. So that just became that part right there. This became this whole part right here. Is that right? Okay. Okay, now let's go solve for x. Right, so maybe add this term over. Mu mg x equals 1/2 m d sub a squared. Like that. Try to solve for braking distance. Oh, what's going to cancel out on both sides? The mass of the car, right? Which is also consistent with the story last time I told you the story. Oh, yeah, you have a question? Or, yeah. Right, so remember last time I told you the story, I said, what if you have a little sports car and a big old semi truck and they're driving side by side, all else equal, same tire, same road, same initial speed, hit the brakes. They should have the same stopping distance. That's what that step says, the fact that mass cancels out. Okay. So the stopping distance is just the initial speed squared. I gotta divide by 2, and then the mu and the g I have to divide down here. Okay. That is the answer to the question, what is the stopping distance? There's not a space for that on the table that I printed out, but that's what that would be. Okay, let's get that. Oh, what if you do this? What if you're in a car driving and you triple your speed? Do you think it's going to take more stopping distance if you're going three times as fast? Yes. Here, guys, folks here. But how does that translate? It doesn't take 3 times the distance to brake. It takes how many times the distance? 9. Because if you throw a factor of 3 on this V naught, see how it would be like 9 times the distance, right? And if you didn't quite see that, remember this is an old story, but here, do you guys remember a trick I showed you recently? Which is that if this is true in general, then it should be true for any specific numbers. So for example, if what if the speed of the car was 1 meter per second, the coefficient of friction was like 1/2, it's like 0.5, and let's say the gravity field, let's say it's a little tiny moon somewhere, it's like 1 meter per second squared. Right? Wouldn't it take 1 meter to come to a full stop? Wouldn't that balance? Right. Okay, so then on this, say, moon that has very weak gravity, what if you triple the speed of the car? 2, 1/2, 1. Right. What's that equal to? like 9 meters. You guys see that? Right. Right. So when you guys are out driving, if you double your speed from like 20 to 40 miles an hour, it would require 4 times the braking distance. And if you triple your speed from 20 to 60 miles an hour, it would take 9 times the braking distance. That's pretty cool, isn't it? Right. And I want to show you guys how this is consistent with the old way we do it. This is the new way we do it. What was the old way we used to solve for the braking distance? Well, what we would do is say free body diagram, car, initial speed, weight, normal force, which is equivalent to the weight, friction force, which is coefficient of friction times normal force, which is coefficient of friction times mg. Okay. Then the rate the car can slow down, that's called acceleration, is net force acting on some mass. That's Newton's second law of motion. The net force is the friction force, which is this expression. So you go, pop that in right there. So the acceleration is mu mg acting on some mass. Mass cancels. And the rate the car can slow down is coefficient of friction times gravity. Okay. Then, after you figured out all that using Newton's second law of motion, so free body diagram, Newton's second law of motion, then you flip this back over to kinematic motion. You guys remember tax VV? And you say, well, here's the rate the car can slow down. So that's mu g. I'll also make it negative since it's slowed down, but that's magnitude. We're trying to figure out braking distance. If the car starts at some speed v naught and goes to, what would final speed be if it's coming to a stop? 0, right? Then you go equation shopping and say, okay, I've got kinematic question. What is x if you know a and the two v's? Wouldn't that just be this last one right here? Right. So then take that one. Final velocity squared equals initial velocity squared plus 2ax. Right, we're solving for x. This goes to 0 from whatever speed it was going, plus 2 times negative mu g times x. Add this over, 2 mu g x equals v naught squared, and then divide both sides by 2 mu g. Get x is v naught squared on 2 mu g. Okay. That was the old way we used to do it. Okay. Look how long that process took. I mean, I barely fit it onto a page of paper, but start with the free body diagram, to do second law of motion, get the acceleration, flip back over to kinematic motion, figure out which equation is going to get us there, plug stuff in, do a bunch of algebra. Whew. And finally, at the end of that very long process, we figured out the braking distance. Okay? But look at the new way we did it. This energy minus this work goes to 0, chug, 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 done. So the new way of doing it, arguably a bit faster, a bit easier, but gives you the same answer, doesn't it? All right. Next one. Ooh, here's a good one. A spring fires a block of some mass m onto a frictionless track. Okay. So from here on out, all these systems are closed systems. So that's nice. What objects matter in this system? What's one of them? So what? Okay, yeah, the spring matters. There'd be energy stored in the spring, so that's definitely part of it. What else? How about the block itself? Because the block is changing height, changing speed. And also, hey, the fact that it changes height, what else must also be important? Okay, I'm thinking like gravity, earth, something like that. Now, if you thought the track, that actually would be a good candidate. I'm not going to include the track, and here's why. So, is there a force from the track on the block? Yeah, and that's a normal force, right? A normal force. Right? So, does that track do work on the block? Well, no, because by definition, isn't normal force always perpendicular to the surface, right? And to do work on something, remember you have to have parallel components. That's what this dot product means. You guys remember that? You guys remember the example of if you're carrying a textbook horizontally across the room, your upward applied force and that horizontal motion have nothing to do with each other. That would be 0 joules of work. So same story here. So if you thought the track, that was a good thought, but it doesn't actually do any work on the block. Energy at point A. Hey, this block started off compressed against the spring, smashed against that spring. What kind of energy? Yes, spring potential energy, which is this one right here. Spring potential energy. Okay? So it starts off with all 1/2 kx squared. Okay? By the time it gets to point B, well, the energy is translated into two different things. So what's one of them? I mean, the spring's unsprung, so there's no more energy in the spring. It's gone into the into the block. Now this block, the fact that it had to have been lifted against gravity, it's changed its height. Did it acquire some potential energy?
Yes.
MGH? Yeah. Right. How about this? Is this block in motion? Does it have some speed? B. Right. Well, if you think about the geometry of this, it has to, because the only way to make it through that loop in the first place is it had to have had sufficient speed to make it around. And the track is frictionless. Yeah, it better have some kinetic energy also. 1/2 mv squared. Okay. And that would be at point B. Wonder if we can solve for that speed at point B. So sum of energy at point A is equal to sum of energy at point B. Just energy is conserved. At point A, it's all 1/2 kx squared. And at point B, well, that energy went two ways. Right? Had to lift the block against gravity, so had to do work lifting it, so that's your MGH. Right? And whatever was left over would be going to its speed. So 1/2 mv squared at point B. Just like that. Okay, so that's the whole energy setup. If you want to solve for the speed at point B, then let's just do some algebra. So you guys do see three terms. I'm gonna take the MGH term, subtract it over, and that'll leave you with 1/2 mvb squared equals 1/2 kx squared minus MGH. Okay. Multiply both sides by 2, so mvb squared equals kx squared minus 2 MGH. Divide both sides by m. vb squared equals kx squared on m minus 2gh. And then finally, take the square root. That's the answer. All right, so remember, there's a few parts of this process. One part is identifying what are the energy bits at point A and point B, then equating those, creating a conservation of energy equation, then identifying, well, what are we trying to solve for, and then just doing there was that giant algebra process. It looks like 4 or 5 steps, algebra process. I mean, it's good to know algebra for this class. Hopefully your skills will get better at that. But then last thing I want to do is make sure that this makes sense. So what if, let's play around with some variables. What if you had a stiffer spring and you compressed it even more? So K is increasing, X is increasing. What is happening to the speed at point B if you have a more heavy duty spring? Things going faster? Kind of makes sense, doesn't it? Hey, like more stiff spring and you squash it more, it's gonna go spring out faster. Right? How about this? What if you increase the mass of the block? What if you replace, what if you start with a little golf ball down here? You replace that golf ball with a bowling ball, something like incredibly heavy. Do you think that bowling ball's going to go faster or slower by the time it gets up here? Definitely slower. In fact, it might not even make it, right? That's consistent with this too, isn't it? Look at that inverse type relationship. Yeah, I see that. Or how about this? What if you took this track and you worked it so that this height change actually increased, like that, the height change increased. What would that do to the speed of point B now that it has to climb a higher hill? It's going slower, isn't it? Look at that, subtracting off something about h. Yeah. So that checks out. I can believe that equation. Square root kx squared on m minus 2gh. I can believe that. Right. A bungee jumper dives off a platform and barely touches the ground before the cord retracts. I'm I'm thinking 3 objects in the system. What's one of them? The jumper? The Earth, because there's a height change, right? Gravity force doing work up and down. So the whole Earth, gravitational mass. And also I'm looking for something else. Yes, the bungee cord. The bungee cord. Okay. Reason being, we're going to treat this bungee. That was a little bit tricky. See if you guys get that. But you guys did. We're going to treat the bungee cord as a spring, and we're going to assume that it follows Hooke's law, F equals kx, all that stuff. So at point A, the jumper is looking up there. He's about to dive off. Right. Oh, I forgot I read that word dive. I made this a long time in the past. Well, we're going to say steps off, I guess. Right. Does he start off with just what kind of energy? Yeah, potential energy, gravitational potential, MGH. Right. If you assume that he actually dove off, yeah, I forgot he did that. Right. You could add a kinetic energy term, 1/2 mv squared, but let's not worry about that. Then he's falling, faster. And then that bungee cord starts to stretch. It goes slower, until he gets to point B and just barely, boop, just touches the sidewalk beneath him before it gets pulled back up. So what would his speed at point B be? 0, right? Yeah, because he's turning around. That's actually the answer to this question, 0 meters per second. But for the energy conservation, because there could be other questions you might ask, right? Where did all the energy go at point B? I mean, there's no kinetic because 0 speed, but there's also no potential energy because he's basically at ground level. So where'd all the energy go? Into the cord, into the spring, exactly. And that is, yeah, you guys are getting this. That's this right here, isn't it? 1/2 kx squared. Okay. So that k represents the thing, kind of like the elasticity of the bungee cord, right? Like how springy it is, right? And x, so the more stiff the bungee cord, the higher the value that k is, right? And then that x represents how much it stretches beyond its initial stretch length. You could equate this to and solve for something like there's 5 variables floating around. So if you knew 4 of those, you wanted to solve for the 5th one, you could do that. Right, single elevator outwood. Right. Actually, the next 2 problems involve some version of outwood, right? There's the classic double elevator, and there's the modified single elevator. Right. Now, the one we're about to do, I'm going to take you guys through 2 processes to get to the answer. We'll do this conservation of energy method, and then we'll go back and do the old way, just like we did with the car braking to stop. And I'll show you guys that it's also self-consistent. I mean, that's true of a lot of these anyway. But what objects do you think are relevant in this one? What's one of the relevant objects? M1, M2, and the Earth. That's it. M1, 2, and the Earth. Okay. Oh, okay. Now here's where you have to apply your imagination a bit. What type of energy at point A? You guys are saying potential? You guys are exactly right. Yeah, exactly right. The fact that M2 is going to fall some distance x, right? It's going to fall some distance x and drag M1 along for the ride. Right? Well, it must be some height above some ground level. Let's call point B. Let's define that as like the ground. Right? So would it be M2 is raised some height above the ground, so it has some MGH? Oh, I shouldn't have said H. I should have said X. M2GX, because I labeled this X. Rid of that one. Because I said X here, right? Just keep it consistent with the picture. Okay. Now, by the time M2 falls that level, it's at ground level, or about to hit the ground, so it has no more potential energy. But is it in motion? Yeah, I mean, it's been building up speed up to that point. So it better have some of this kind of energy, right? But you know what? It's tied to M1. And isn't M1 also always going at the exact same speed? Because they're tied together? So some of the energy was diverted into pulling M1 along for the ride. And they have the same speed. Guess that? So this kind of energy turns into, well, it splits between those 2 blocks. Right, so what is the speed of the system by the time it falls that distance x? Well, let's find out. So same process we've been doing. Sum of energy at point A is equal to sum of energy at point B because energy is conserved. At point A, it's all, so you guys can see this. Come on. At point A, it's all M2GX, where X is the eventual drop height. At point B, well, there's no more potential energy, but it's all 1/2 m1 v² plus 1/2 m2 v². Just like that. Okay. Turn that. All right, guys good? All right, then, hey, does it look like we could factor out the VB² just to consolidate that variable that we're trying to solve for anyway? Maybe I'll do that. M2GX equals, well, we've got 1/2. When you factor it out, it's gonna look like this. The sum of the masses, then VB squared like that. Okay, so now the variable we're solving for, instead of being in two places, now it's just in one place. So that looks a little cleaner. Okay. Oh, so finish this thing off. Looks like I'm gonna multiply both sides by 2, then divide down the sum of the masses, then take the square root. Okay. Do this one at a time. So I'll switch to left and right side while I'm at it. So first, multiply both sides by 2. That would look like this. Then divide both sides by the sum of the masses. So I'm just taking this and dividing it down here. So that's going to look like VB² is 2m2gx divided by sum of the masses. Okay. And then, oh, finally, take this, what's the very last step? Square root. So the speed at point B is the square root of this fun expression. Okay, so that is the answer to this question. What's the speed at point B? Well, it's this giant square root. 2m2gx over sum of the masses. Okay. Again, I never want you guys to like lose yourself in the woods doing these problems. So let's see. Remember what you guys are trying to solve and how this is all consistent. Okay. So here's the energy at point A, energy at point B. They have to equate. We did a bunch of algebra to figure out the speed, and it's this crazy expression. But does this expression make sense? Right. Well, let's test it out. Let's poke around a little bit. So what if mass 1 was 0? What if mass 1 is just 0 kilograms? Wouldn't mass 2 just be in perfect free fall? Right? And how does that translate to this equation? If mass 1 goes to 0, doesn't this go away? 0. And then, oh, what's m2 over m2? That cancels. So wouldn't you just have square root of 2gx? Oh, square root 2gx! That's the same thing as the Galileo problem, which is perfect free flow. So it's all consistent? It's all good, right? Okay. Yeah, you can do other things with that, but that's a good example there. Okay. And I told you I wanted to do one other thing with this, is show you how we used to solve this, because you could actually get the same answer before conservation of energy. And I'll show you guys how you would do that. Back when you guys did this lab, you said the acceleration of that system, net force on total mass. Hey, that's Newton's second law of motion, isn't it? The acceleration of that particular system, well, what's providing the net force? Isn't it just the weight of M2 pulling down? So that'd be M2G, because that's that weight. And then the total inertia being pulled around is the sum of the masses. Okay, so that right there is the acceleration of, well, M2 down or M1 to the side. Okay. Then you'd have, if you want to figure out the question, what's the speed at the end of some interval, you have to go back to kinematic motion. Here's the formula we used before. We're just going to use it again. It's that third kinematic formula. F squared equals v naught squared plus 2ax. Okay. Substitute this expression for the acceleration right there. And it started from rest. This number just goes to 0 meters per second. What have we got? The speed at the end squared is equal to, say, 2ax. So it's 2 times, here's a, it's this big old fancy expression for that outward, modified outward, all times the drop height. Okay. So VF is just the square root of that. So the square root, and while I'm at it, I'll go ahead and take the 2 and the x and just pop them in that numerator. So it's going to go 2 M2GX on sum of the masses. That was the old way of doing it. And I did it a little bit fast just because you guys have seen that before and it's not the point of what we're doing today. But the reason I did it is because, hey, look at that. It's the exact same things we got using conservation of energy. It's the same thing. Different approach. So let's do, oh, here it is on the side. Here's the old approach. This is the new approach. Here's the old approach. Same answer. Okay. Let's do the other, the classic double elevator outlet. Okay. Now this one will just do conservation of energy. What objects do you think are important to this closed system? I think it's the same as before. Probably each block and the Earth. Yeah. Each block because those blocks moving around, they're changing height, changing speed. The Earth because, well, that's providing a force moving the system. And there's a height change. So the sum of energy at point A equals the sum of energy at point B. Well, just got to figure out what those energies are. Okay. All right. This is a little trickier than the last one we did, but maybe you can kind of figure it out. What do you think I should put in this box? Where's the energy coming from? What's supplying the energy? Suppose it goes clockwise. It's going clockwise here. You guys see M2 is falling and M1 is rising at the same time? You see that? The fact that M2 is falling, that means it had to have started with what kind of energy? Potential energy, gravitational potential energy, this one right here. So M2GH, and I'll go back and call this H because that's what I have it labeled. Okay. That is actually supplying all the energy for the system to move at all from this point of view. Okay. Now that system went 3 different places. I wonder if you guys can figure out the 3 places that energy went by the time these blocks switched and go to point B, like that. What's one place that energy went? How about M2 lifting M1? Did it lift M1? Yeah, M1GH. And it's the same H, isn't it? However far down block 2 went, block 1 went at the same height. And oh, didn't each block also acquire some speed? So should I say plus 1/2 mv squared plus 1/2 mv squared, except for block 1, block 2? Okay. At point B, okay, that right there is going to be the conservation of energy setup. This term equals the sum of these 3 terms. Okay. Here's where the energy came from. Here's where it went to. So M2GH, the block falling, provides the energy to lift block 1 and also give each block some speed by the time it gets to point B. Okay. All right, so we're gonna set physics aside for a moment and just do a bunch of algebra. So maybe factor out the, do 2 things at once. I'm gonna slide the M1GH over. So M2GH minus M1GH. At the same time, I'm gonna factor out this BD squared. So 1/2 sum of the masses, BD squared, like that. Okay, so that's a couple of things. Okay. Then multiply both sides by 2, divide both sides by the sum of the masses. So VB squared equals, okay, multiply both sides by 2, divide by the sum of the masses. What else goes in the numerator? Well, the difference of the weights. And here I'm also going to factor out the GH, so that'd be M2 minus M1, GH like that. Okay. Yeah, I threw a few algebra steps in there, but that's what that would be. Then last step, square root. 2 times difference of masses, GH over the sum of the masses. Just like that. That's the answer. So it goes, BB is giant square root 2 times the difference of the masses, GH divided by the sum of the masses. Like that. Oh, look at how this one turned out compared to the last answer. The last answer versus this answer. They look pretty similar to each other, don't they? Like same type structure. Or what if you did this? Remember we've been making some thought experiments? poking around testing these formulas. Okay. What would happen if you took M1 and made it 0 kilograms? 0 kilograms. Wouldn't M2 just be perfect free fall? Okay. How does this equation play out? So if M1 is 0 kilograms, that 0 goes away. M2 over M2 is just 1. Oh, we're back to square root 2gh. Like Galileo dropping stuff off the tower. Okay. Or what about this? What if they're the same? Like 200 grams and 200 grams, if they're the same? What does that system do? This sits at rest, doesn't it? Right? Take the difference of same thing, that zeroes out, doesn't it? Yeah. Okay. We're just going to do 2 more of these today. Spring fires a ball vertically to some maximum height. What's in the system? We've got, did I show you guys hydraulic jumps yet? Okay, so here, this is all back. We got the ball, the earth, and the spring. The energy at point A is all in the spring. It's like spring loaded. And by the time it reaches the maximum height, it's turned to energy at height, that's potential energy. But there's no more speed. Now there's speed in the middle. Right? So the middle has kinetic energy during the transition, but at point A and point B, there's no kinetic energy. Therefore, what's the speed at point B? 0 meters per second. Right? Now you could solve for other things. Like you could equate this to this, and if you knew, I see 5 variables, point. If you knew any 4 of those, you could solve for the unknown fifth. Like you could solve for maximum height if you knew the spring constant, or vice versa. How about this? What if a block falls onto a spring? And I did in parentheses say, assume no mechanical energy lost during collision. That detail is important for a future topic called conservation of momentum, which involves collisions, but we're going to ignore that for now. This looks like the same thing, just in reverse, doesn't it? You got a ball, the earth, and the spring. Now this one, it starts off with all potential energy mgh. Then when it smashes that spring, the energy at some point would all go into the spring, 1/2 kx squared. But what would the speed be at the maximum compression value? Also 0, right? Is that true? You guys get that?